All right, let's talk about a classic C++ head scratcher. It's one of those things that seems so simple on the surface, something you've probably done 100 times, but it hides a really surprising secret, one that can lead to some seriously nasty bugs if you're not paying attention.
So the question is this: how do you actually hand an array over to a C++ function? It seems pretty basic, right? You've got a collection of data, and you just want another piece of code to do something with it. But as you're about to see, the C++ answer is where things get really interesting. Okay, so let's set the scene with a super common scenario. Imagine you have an array, maybe a list of scores, sitting there in your main program. All you want to do is pass it to a function, maybe to print them out or calculate an average. Sounds totally straightforward.
So, you'd write some code that looks pretty much like this. You define your scores array, and then you call your printArray function, passing scores right into it. I mean, it looks clean, it makes perfect sense, but what is the compiler really doing behind the scenes? And this brings us right to the heart of the matter. You think you're telling the compiler one thing, but it's actually hearing something a little bit different. And this whole phenomenon has a cool, kind of dramatic name: array decay.
Now, take a look at this. On the left, you see the function we think we're writing, one that takes an array. But on the right is what the compiler actually understands, a function that just takes a pointer to an integer. And get this, to the compiler, these two are exactly the same thing. That array syntax is just what we call syntactic sugar. It's just a convenient shortcut for a pointer.
So, let's put a formal definition on it. Array decay is simply the process where an array basically loses its arrayness. It just decays into a simple pointer that points to its very first element. The function never gets the whole array, it just gets the memory address of where that array starts.
So what's the big deal? Well, this decay leads directly to the single biggest problem. If the function only gets the starting address, how in the world is it supposed to know where the array ends? The short answer is, it doesn't. All that critical size information is just gone. It's lost in translation, leaving your function totally flying blind.
And here is a trap that so many of us fall into. You might think, oh, I'll just use size of r inside the function to get its length. But nope. Because of array decay, r isn't an array in there anymore. It's just a pointer. So size of is just going to give you the size of a memory address, which is usually 4 or 8 bytes, not the size of all your data. It's exactly like being told the address of the first house on a street, but having absolutely no idea how long the street is.
So how on earth have programmers been dealing with this for decades? Well, they came up with a pretty reliable, if a little manual, way to solve it. This is what we call the classic C-style solution.
The fix is basically a two-part deal. First, you just accept that you're only passing a pointer. Then, to make up for that lost information, you explicitly pass the size of the array as a completely separate second argument. You give it the starting address, and you tell it how far to go.
And in your actual code, that looks like this. Your function signature changes to accept not only the array, which, is really a pointer, but also a second integer for the size. Now, this totally works, but it puts all the responsibility right on your shoulders, the programmer, to always get that size right. One little mistake and you're looking at crashes or some really weird bugs.
Thankfully, we don't have to live like that anymore. Modern C++ gives us much better tools. These solutions are just designed from the ground up to be safer, smarter, and way less likely to cause these kinds of errors.
The standard library is your best friend here. It gives us awesome containers like stdvector for when your array needs to change size, and stdarray for when the size is fixed. And the one killer feature they all share is simple but so powerful. They always know their own size. That information is bundled right in with the data itself.
And this table just lays it all out perfectly. The old C-style array doesn't know its size, and it suffers from pointer decay. But look at stdvector and stdarray, they both know their size, and you can pass them by reference, which completely avoids the whole decay problem. stdvector is your go-to for dynamic lists, while stdarray is a super efficient, safe replacement for those old fixed-size C arrays.
So really, the most crucial thing to take away from all this is that when you use modern C++ containers, you're not just moving raw data around anymore. You're passing these smart objects that manage the data for you. And that simple change in how you think about it just wipes out an entire category of common bugs right off the map.
Okay, so we've pretty much cracked the code for a simple one-dimensional list of numbers. But that just opens up an even deeper question, doesn't it? What happens when you have an array of arrays, like a 2D grid? Does decay happen again? Well, the challenges definitely multiply.
But that's a story for another time.